Yes.
Yes.
Yes. For some. Okay, great. So the agenda today is that we will first recap what we discussed yesterday for about 15 minutes, and then we'll look at some covering problems. So although the schedule says feasibility problems, but I realize that before feasibility problems, it may be a good idea to look at covering problems. So feasibility problems, we are going to shift it to day 4. And today we are going to look at covering problems. After the doubt clearance session. So if you have any doubts regarding what we discussed yesterday, you can ask me, or you can have any, you may want to make any comments. You can make comments if you like. Okay, so let us recap what we did in 10 minutes or so. So we had this load balancing question. So the input was a set of n tasks. So each task had some duration. So this duration is also called load. So duration means load. And these tasks have to be assigned to m students. Okay. So what was the goal? To assign the task such that the maximum workload on any student is minimized. And we discussed this question, and a possible algorithm was suggested. So the algorithm was the following. That first sort the tasks in decreasing order of load. And then assign the tasks one by one according to this order while maximizing welfare. So what is welfare maximization? It is assigning the next task to that student who is the least loaded at that time. Let's say assigning the task at hand to the least loaded. Student. So we argued with some effort, some discussion, some trial and error that this algorithm is a 2 approximation, but today we'll argue that this is actually a 3/2 approximation as well. So 3/2 approximation means the load that this algorithm will assign to the most loaded student is at most 3 by 2 times more than the optimal max load by any assignment. So appreciate that 2 approximation is poorer than 3 by 2 approximation. So 3 by 2 approximation means that you are saying something more useful. You are saying something stronger, that okay, this algorithm is not a 2 approximation, but it is even better than a 2 approximation. It is a 3 by 2 approximation. So is there any doubt on why 3 by 2 approximation is considered better than 2 approximation? Okay. So everyone is convinced that if we can prove that for a minimization problem, we have a 3 by 2 approximation, then that is saying something stronger than saying that it's a 2 approximation. Okay. So now we also said that to compare the quality of the solution with the optimal solution, we need to find a lower bound on the optimal. And to do so, we had made certain observations. So anybody recalls what is the first observation?
Optimal is at least maximum over all eyes LIs.
Yes, so whatever is the assignment, at least one student will get the task which has the maximum duration. So there will be at least one student whose load is at least the max duration among the tasks. So let us introduce the notation again. So let us say task I has duration Ti. So then the observation was that OPT must be at least max of Ti for all I. So if there, let us say how many tasks we had? We had n tasks and we had m students. So if you take max over all tasks, so I'll say for all I in 1 through n, OPT has to be at least the duration of the max task, because that load must be borne by some student. So this was observation 1. So what was observation 2?
So that was the OPT was greater than or equals to the capital T by M, and wherein the capital T was the sum of the durations of all the tasks.
Very nice, yes. So it denoted by capital T the sum of the duration of all tasks. So we said, what is the average load? So the average load is the total duration divided by the number of students. So at least some student must have average load by pigeonhole principle. Because if all students have less than average load, then all the tasks are not carried out. All the tasks are not executed. So with this notation of T, we said that OPT is at least T by number of students is M. So these two lower bounds we had. Now, these two lower bounds enabled us to argue a 2 approximation, but we want to argue a better approximation, 3/2 approximation. And to do that, we have to make some more observation. Uh, so let me not waste time and tell you what needs to be done. So case 1 is that if the number of tasks is strictly less than the number of students, then no student gets more than one task. That is by virtue of our algorithm. Our algorithm is greedy and it does not give a task to someone who is already loaded. It always gives a task to the least loaded person. And since there are less than can get because screen share stop.
Yes, sir. It's not visible.
It's good now.
Yeah. Yes, sir.
Okay, if the number of tasks is strictly less than the number of students, then by virtue of the greediness of our algorithm, no student gets more than one task. So in that case, what is the max load on any student? This quantity. And that is also equal to OPT. Therefore, we have an optimal solution. So by observation 1, in this case, we must have an optimal solution. By observation 1, our solution is optimal. Is that fine?
Yes.
So after that, we'll have to say some more things, some more technical things, but this thing is straightforward. If you don't understand this part, then the following things you will not understand. So if you have not understood yet, you can raise your hand, you can let me know. I'll repeat the argument. Because without this argument, the following arguments will not be understandable. Yeah, so this is less than equal to. Right? So even if there are exactly equal number of tasks as the number of students, then also no student can get 2 tasks. So let's take case 2. So in case 2, there are at least m-1 tasks, at least one more task than the number of students. Okay, so n is strictly greater than n. So that means that there exists the m plus 1th task. it exists. And because it exists, at least one student must get 2 tasks. So far, so good. Fine. So now we'll make one observation. So let us say that our algorithm assigned the tasks and the student who got the highest load is student J. So SJ received the highest load. By our algorithm, this greedy algorithm that we have. So recall that our algorithm is 2 steps. We process the tasks in decreasing order of the load, and then we assign the task at hand to the least loaded student. That's all we do. So with that strategy, there was a student SJ, and she has received the maximum load. So the way we show it schematically with a diagram, let us show that. This is the load. And let us say the last job student J has received, it has duration tau. So let us say total load on SJ was LJ. So then the rest of the tasks have duration LJ minus tau. So LJ was total load. On student SJ. So, so it can very well happen that tau is in fact the m plus 1th task. So it can very well happen that tau is the m plus 1th task, and tau itself is equal to the duration of the m plus 1th task. So the first m tasks are being given like as a first task to any student. So since this tau task was not the first task that SJ has received, so tau could very well be the m plus 1th task, or it could be something which has come after the m plus 1th task, something which has been assigned, which has been processed after the m plus 1th task. But we have processed the tasks in decreasing order of duration. Therefore, tau would be at most Tm plus m plus 1. Is that fine?
Yes, yes.
So, Mr. Goel, do you understand why tau is at most Tm plus 1?
Yes.
Okay. So consider an optimal solution. So in an optimal solution, there is at least one student who has received 2 tasks. Okay. Because there are more than m tasks. since there are more than m tasks and there are only m students, so even in the optimal solution, there is one student who has received more than one task. There is at least one student who has received more than one task. So what is the load on that student? So I want to get a new lower bound on OPT. So I'm going to write it down. Okay. So there exists a one student even in the optimal solution who received more than one task. So what is the load on him? So that student must have received one task. So let us say task 1, he has received task 1 plus task 2, let us say. So the task 1 is one of the first 1 to m tasks. Okay. So if he has received 2 tasks, then the first task must have been one of the first 1 to m tasks, because greedily we are not allowing any student to go empty when the first m tasks are being assigned. So that task 1 had duration at least tm plus 1. So we are processing the tasks in decreasing order of load. So tm plus 1 is the m plus 1th task. And because the task that was first assigned to this student, he must have received a task which is at least tm plus 1. Okay. Now consider that student in the optimal solution who has received the m plus 1th task on top of something else. So that student who has received this task on top of the task that was assigned to him while assigning the 1 to m tasks. So what is the load? What is the duration of the task 2 for that student? That is again tm plus 1. So m plus 1th task he has received, but previously he has received another task which was at least duration tm plus 1. So that means OPT has a student whose load is at least 2 times tm plus 1. Does this make sense?
Yes.
All right. Okay. So what do you know? You know that in your solution, the person who had got the maximum load Sj, he had some load tau and rest of the load Lj minus tau. So tau is upper bounded by Tm plus 1 and Tm plus 1 is upper bounded by OPT by 2. So from here, what shall we write? From here, we will write that Tm plus 1 is upper bounded by OPT by 2. So we are moving this 2 down here. Since OPT is greater than equal to 2 Tm plus 1, then Tm plus 1 is at most OPT by 2. So now we have additional observation. So we know that the last task that our student, our heavily loaded, most loaded student has received is at most OPT by 2. from here. Let us say this is, I don't know, let us say this is theta. So from theta. All right. Rest of the argument is same. Rest of the argument is same. Yes, go ahead, Indrani.
Sir, I just wanted to check, is anyone else facing some network issues after every 30 for a few seconds, about 7 to 8 seconds, I'm not able to hear anything. Then I'm automatically again connected. And this is happening since the last time I couldn't see the screen.
No, I'm not facing any network issue. For me, things are fine.
Oh, okay.
Okay.
Uh,
That is very sad to know. Is there anything I can do on my part? So is there anybody else who has this issue? So everybody else is able to get a normal connection. I mean, they have as usual connectivity.
If I'm able to see anything, so, I mean,
Mohan, Mohan, you have something to say?
no, sir, like we are able to see. I mean,
Okay, fine. All right. So I don't know. Then I don't know if it is a problem on my side. So Indranil, you are able to hear me now properly. Okay, I think he has dropped. All right. So this is the crux of the argument.
so, but I have a small doubt here that so why to call this SJ as a heavily loaded one? Quite possible that the SJ might have received the last task and still lots of scope is remaining with SJ to include a few more tasks to become equals to the maximum duration.
So this is the assumption. So this is, let us say, it is, we are not, so what is the question you're asking?
Uh, so if in case if we consider that SJ has received the highest load,
No, that is what we are
then
assuming. That is an
okay,
assumption.
okay. So if we make this assumption, then why to consider that the additional task is going to be assigned to SJ only? If the
Okay,
number
okay.
of the okay, yeah.
I understand what so you are saying that why SJ has received more than one task? That is the question.
Yes,
So if SJ has not received more than one task, if SJ has received only one task, and it is the, by assumption, most loaded person, okay, then everybody else have less load than this person.
yes,
But this is the most loaded person, and he has received only one task. So that means he has received the uh, 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 max of TI.
yes,
Now, I know for a fact that the optimal solution cannot have load, max load less than max of TI
yes,
from observation one. So then
yes,
optimal solution and our solution are equally good. Then we have a
yes,
one approximation. We have an optimal solution means one approximation. So then one approximation is also a 3/2 approximation, right? Now, if you are saying that something is optimally solved, then that is by default 3/2. So if I'm telling you, so you understand that finding the optimal solution is also getting a 10 approximation. Because at the most you have been off by 3/2 factor. That is the meaning of 3/2 approximation. Now I am saying that you have got an optimal solution. So you are off by at most one factor. That is contained within the statement that you are at the most 3/2 factor off.
Yes.
So remember what we discussed yesterday. So if we want to minimize time and if we have taken the flight, then we have an optimal solution. But if I say that no, I have reached Guwahati from Bangalore in at most 3/2 the best time, then that is also right because I took the
Yes.
flight.
Yes. But here, if so, I'm considering case 2 wherein n is greater than m. So this additional task could have been given to someone else also. I mean, by following
No,
the policy of the.
additional task is definitely given to someone else. So this is the max load task. So this is max of Pi. And because this is a max load task, this task has been performed by somebody in the optimal solution as well. There is no doubt about it.
Mhm.
Now, I have already assumed that I do not know whatever the other assignments are. But by assumption, this student has received the highest load. So even if other tasks, many tasks have gone to other students, but their height, I mean, the loads, overall load, even if so multiple tasks could be small tasks, and they may not, the sum of the small tasks together may not exceed the max of the this task. So the max
Yes.
load is still this guy. The max load is still suffered, still borne by student SJ.
Mhm.
So in any case, we are not doing any worse than the optimal. So if you would have been right in so let me put it this way. You would have justified reason to complain if there were other students who had got multiple tasks but exceeding the overall load on SJ. Then you would have reason to complain. But that is already ruled out by the assumption. This assumption that SJ himself or herself has received the highest load by our algorithm. So our algorithm's quality is defined by the load on SJ. That is the max load on any student we have given. So such a thing will not arise. Such things can arise. Not exceeding this upper bound defined by the load on SJ.
Yes. So what I understood from this discussion is that basically we are performing some worst case analysis kind of a thing by assuming that the additional one is intentionally is given to the one who is already heavily loaded, just to check the strength of the student SJ, how much additional can this student bear uh, apart from uh, the maximum load. So probably this will give us an upper bound of the approximation.
This is not probably, this is definitely, this is a mathematical truth. There is no, this deterministic statement. There is no probability or randomization involved.
Okay, okay, okay.
With
Yeah.
probability 1, whatever we are saying is correct.
Yes, yes, understood. Yeah.
Anybody has the same doubt or anything that is not clear? So we have made this additional observation. The tau, the last job, which is received by the max loaded job, if at all he has received anything. If the max loaded student has received only one job, then we already have an optimal solution. If not, then the max loaded student he has received multiple jobs, multiple tasks. And the last task he has received has duration tau. And we are getting an upper bound on that last task, and we're saying that it is at most OPT by 2 with the help of this observation. So now the rest of the things that this student has got LJ minus tau was again at most OPT by our discussion last time. So overall OPT plus half OPT, we have a max load of 3 by 2 OPT. So let us recall this remaining load, why that is OPT. Let us recall that argument. So the moment, so that the point in time when the last job was assigned to this student was least loaded. So that means this student has had a load of LJ minus tau, and everybody also had a load of at least LJ minus tau. So at that time, the total duration of the tasks already distributed, already assigned, was the number of students into LJ minus tau already. So this much task was already distributed when at that time when tau was getting assigned to SJ. So that means the total sum of the duration of the tasks is at least this much. Now what do we know? We have said that this quantity, the sum of the duration of the tasks divided by, so what is the observation? 2, that this quantity divided by M is the lower bound on OPT. So T is, so if I take M on this side, so I can take M on this side. I can say M times OPT is at least T. So that is my observation 2. So this is T. This guy is T, right? Some of the duration of the jobs. So M times OPT is at least M times LJ minus tau. So therefore we have what we want, that LJ minus tau is also bounded by OPT, bounded above by OPT. So the remaining tasks is also at most OPT, and tau we have already said that is at most OPT by 2. Therefore, the maximum load on any student, the highest load given by the algorithm is at most OPT plus OPT by 2. All good? So this argument is already yesterday's argument. So therefore, load on our student having highest load is LJ minus tau plus tau. So from above, this is at most OPT plus OPT by 2. So we have a 3 by 2 approximation. Okay. Okay, so we'll change gears. Now we'll look at covering problems. We have 1 hour time. We'll finish by 12:30. In between, we'll take a break of 10 minutes. So I will tell you what is the problem. Before that, is everybody fine with the transition? That 3 by 2 approximation is fine with everybody. Okay, so fine. Great. So let's look at covering. Let's start with a new page. Okay, so let me motivate the question. So suppose this is the, I don't know. map of a city. I mean, this is the boundary of a city. There are uh, some locations in the city. How I should put it? Okay, so people live. So this is not a very densely populated city like the Indian metro cities. So this is like less populated city. Or let us say it includes a city plus the suburbs. Okay. So there are some locations which are highly populated. These locations are highly populated. And in between, there are, let us say, less populated places, maybe some rivers or natural setting or farmlands. Not non-residential things are not uh, marked. So only the highly populated residential locations within this area are marked. Okay. And you are a telecom company. You are the CEO of a telecom company. So you want to set up base stations or towers so that each of the densely populated locations receive signal. Okay. So assume that if you set up a tower, so this is a tower, then it radiates, or rather it gives coverage omnidirectionally. It gives coverage omnidirectionally, but to some extent. So every base station has a circular coverage area. Okay, so if the base station is located here, then with the base station at the center till some radius r, the base station is capable of providing coverage with good quality, with satisfactory quality. So I will draw a better circle. Nothing is working. Just a second. So let's take a different color. Let's make it 4. Okay, now it's visible. So what is your objective? You want to place towers, and placing a tower is equivalent to drawing a circle. For example, if you place a tower here, then you have provided coverage within the circle centered at this location. So you want to place as few towers as possible, such that everybody gets coverage. Everybody means these set of points that we have drawn, which is part of the input. That is the task. Minimize. So how should I put it? So the equivalent formulation in geometry is the following: that given a set P of n points in the plane, cover them. What is covering? Covering means if a point is within a circle, so then it is covered. So for example, these 3 points are within this circle, then we say that this circle covers these 3 points. Cover them by a minimum, or rather by a minimal number of unit circles. So I'm saying unit because you can always scale things up. Okay, so what is a unit circle? Unit circle is a circle with radius 1. Is the question clear? So if the question is not clear, you can let me know. So if the question is clear, you can think about it. Okay, I'll give you some time to think. So okay, so anyway, we'll finish by 12:30. So let's take a 10 minutes break. So 11:22. So let us meet at 11:32. So let us take a break now and we'll resume at 11:32 a.m. Okay. Yeah, let's start again. Sorry, I got delayed. It's fine. So any thoughts what we should do? Any ideas like what one might do? Okay. So will some greedy technique work? So what if I tell you that all the points that you need to cover are located within a 3x3 grid cell? I mean, square. So this is square of side length 3, and the points that you want to cover are all located within this square. And you have to cover them with these unit circles, means radius 1 circles. So you have to minimize the number of circles required, unit radius circles required. I'm giving a special case. Then can we solve it? So observe that any feasible solution, let us say this is a feasible solution. Feasible means that covers all the points. So all the points are getting covered by these 3 unit circles. And we can say something about these circles. So observe that we can, given a feasible solution, we can find an equivalent solution. Okay, so I will tell you what I mean. Given a feasible solution, we can find an equivalent solution with some nice properties. So what is that equivalent solution? So observe that this circle can be shifted, can be translated so that it intersects, its boundary intersects 2 points, 2 input points. So that is sort of like the extreme position of this circle. If you translate it further, then the number of points covered by the circle will decrease. So this circle is responsible for covering these 6 points. So you can translate this circle so that it passes through 2 points. So you can do that for this circle also. So a translation can help you. So it can happen that a circle is passing through multiple points, like in this case, with via multiple points. That is also possible. Okay, so that is one observation, that one can find an equivalent solution with the property that its boundary contains 2 input points. So this is one case. Other cases, it can also happen that you are translating a circle and it was not possible to pass it through 2 points. You could only pass it through 1 point. Sorry. Okay, let's take it. So maybe you are pushing it, and the top boundary of the circle passes through 1 point. Let us say there was a point here. So that is another possibility, that there is no way you can translate a circle that passes through 2 input points. So it passes through, but at least it will pass through 1 point. So let us say that is the top point. Its boundary contains the top point. Or I mean, how I should put it. The top point of the circle is a boundary circle. Is an input point. The top point of this circle is an input point. Okay. So we can do this translation. So it is possible to translate the circles in any feasible solution so that they satisfy one of these 2 properties, that either a circle is passing through 2 points or it is passing through 1 point, that is the top point. We can do this translation, right? So that means every feasible solution can be constructed by picking circles from a number of candidate circles. So a number of candidate circles can be identified for covering these points. So far, so good. Now consider a pair of input points. So if 2 input points are more than 2 distance apart, if the distance between 2 input points is more than 2, then you cannot draw a unit radius circle such that these 2 points lie on the boundary of the circle. So if they are more than 2 distance apart, then that is an invalid case. Then we don't have to worry about it. Okay, but if the 2 points are nearby, less than 2 distance apart, then we can define possibly 2 circles that pass through these 2 points like this. Correct. Pair of point defines 2 candidate circles. Every pair of point which are at most 2 distance apart. or less than 2 distance apart, I should say. Equal to 2 will not be. Actually, equal to 2. Equal to 2 means one circle. Like the 2 points are diametrically opposite. That is the other case, that the top point is an input point. Let us say less than 2. So let us say less than 2. If 2 points are less than 2 distance apart, which is less than 2 distance apart, defines 2 candidate circles. Yeah. And every 1 point can define 1 candidate circle if this point is the top point of the circle, like this. So by the second case, that if the point is the top point of the circle, then additionally there exists 1 circle per input point, 1 candidate circle. Okay. So for covering this set of points, within this 3 cross 3 squares, how many candidate circles you have of that satisfy one of these 2 properties? So how many candidate circles do we have? Yeah. Anybody? We just calculated it. So every pair defines 2 circles. So 2 times the number of pairs and choose to plus n at most, because if 2 points are more than 2 distance apart, then that is an invalid scenario. So the number of candidate circles is at most this quantity. So which is order n squared. Because n choose 2 is n into n minus 1 by 2, and then you have multiplied by 2 plus n. So 2 cancels out, this term is order n squared. So you have at most order n squared candidate circles to check. Okay. So additionally, you know that to cover the points within this small area, 3 cross 3 area, how many circles will always suffice? So the question is, to cover points within this circle, 3 cross within this square, 3 cross 3 square, how many radius 1 circle will always suffice? That more than that is definitely not necessary. Any thoughts? What is the total area of a 3 cross 3 square? 9. Now, so what is the smallest square that can fit in within a 1 radius circle? So let us be generous. Let us, so you know that the smallest circle, largest circle that can fit inside 1 radius. Let's put it this way. So the largest, let's take a different picture. So the largest square that can fit inside a 1 radius circle has its diagonal length 2. Okay. So we know for a fact that the side length of the square is greater than 1. Because by the Pythagorean theorem, if the side length was 1, 1, then this would have been root 2. But this is more than root 2, this is 2. So therefore, this length is more than 1, this length is also more than 1. So that means that if you divide this 3 cross 3 square into 9 parts like this grid, then for each square which is having side length 1, you can take a circle of radius 1 which totally covers everything inside this grid cell. Okay, so 9, 3 into 3, 9 1 radius circles will always suffice, you know for a fact. Okay, but your candidate set is only ordered n squared. So you can ask that whether I can cover all the points by one circle itself. If it is not possible, then you check whether 2 circles are sufficient. Then you check whether 3 circles are sufficient. And you go on till checking whether 9 circles are sufficient. Out of this, order n squared candidate solutions. Okay. So this gives us a polynomial number of possible covers that we can find. So how many? So is this fine so far? Okay. So the number of candidate solutions, also say cover, is at most the order n squared, choose 9. Okay. So that is order n squared to the 9, so order n to the 80. So in polynomial time, you can solve this question. So one can find. So what is our conclusion? Conclusion is that given a set E of n points within a 3 cross 3 square on the plane. Oh, there is one more thing. So this is the total number of solutions. So now if someone, so one more thing has to be told. that if someone is given a cover, let us say, consisting of 4 circles, then to answer the question whether it is indeed covering all the points, does it cover all the points? To answer that question, some additional time is required. So how much time is that? So you have n points that you have to check whether n points are getting covered or not. And your solution size is 4. That means you have 4 circles. So how much time will it require to answer this question? That whether these 4 circles indeed cover these n points. So for a given point, whether it is contained within a circle or not, that can be verified in constant time. So for every point, you may have to check at most for 4 circles whether this point is contained within it or not. So in 4 into constant time, you can answer whether a point is covered or not. And there are n points. There are n points. So in order 4k time, 4n time, you can answer this question. Now you know that your solution size is also bounded by 9 because you have a 3 cross 3 square. So instead of 4, we will take order 9 in time to answer the question whether a given cover is covering all the points or not. Okay. So this is additional time required. So for every candidate solution, you will need that much time. So overall time that you will require is, so this conclusion is given a set P of n points within a 3 cross 3 square on the plane. One can compute a minimum set of radius 1 circles. I'll push these things slightly below. One can compute a minimum set of radius 1 circles covering P in order n to the 18 into 9n. 9 is again order n. That is order n to the 19 time. So far, any doubts? So say we have only solved the special case that when the points are contained within a 3 cross 3 grid cell. Now we have to solve the general case. So if you don't understand this part, then the general case cannot be dealt with. So maybe on a Sunday you are not feeling like having a long session. So maybe we will just see if there are any questions and take this argument forward in the next session. Because I don't have any feedback so far. Okay, so if you have any doubts or questions, you can ask. I think we can move to the last part of the session, that is feedback and Q&A. All right. If there are no questions, then we will take this argument forward next time. And we will see how using this solution for the special case, one can solve the original problem when the points are distributed all over the plane and you want to find the minimum number of unit circles covering all of them. Okay. Fine, then see you tomorrow, 5 p.m. All right. Thank you. Thanks a lot for joining on a Sunday. I'll see you again.